Uh, Vanakkam and welcome to day 5 of FTP on additive manufacturing from factory floor to the 3D printing to factory floor. The speaker for the session is Dr. Murugayan Amrudalingam, Department of Metallurgical and Materials Engineering, IIT Madras. The topic for the presentation will be controlling microstructural evaluation during wire arc additive manufacturing process. About Dr. Murugayan, Dr. Murugayan is currently associated with the Department of Metallurgical and Materials Engineering at IIT Madras with around 15 years of experience in teaching and research. He completed his BE from University of Madras in 1999, MS by Research from IIT Madras in 2002, and PhD from Delft University of Technology, Netherlands in 2009. Dr. Murugan has carried out 3 sponsored funded projects by ISRO, NBC, Bearing, and IIT Madras. He has also published more than 70 research articles in reputed SE and peer-reviewed journals. He is also acting as reviewer of top 10 international journals in additive manufacturing and manufacturing sector. He has been awarded by many organizations towards his contribution in research. To notify few, first, he is the first and only recipient of Welding Torch of Honor from Delft University of Technology, Netherlands, till 2015. Then Kent earliest Best Paper Award from International Institute of Welding, etc. His research area includes additive manufacturing, welding metallurgy, welding process development, steels product development, in situ 3D synchronized X-ray diffraction. With this brief intro, now I request Dr. Murugan to take over the session. Over to you, sir.
Yeah, thank you, Dr. Dinesh. Welcome to the lecture. So I'm going to talk about the next 1 year, next 1 hour. What we are going to look at is what is a wire arc additive manufacturing and how we can overcome some of the problems we generally encounter in wire arc additive manufacturing. But the problem, what I'm going to say, it is also very common for any other additive manufacturing process. So we will straight away go to the presentation. Let me share my screen. Is my screen visible?
Yes, sir.
Yeah, you see the presentation, right? Yeah.
Yeah.
Okay, so what we are going to look at in next, say, possibly 1 hour or so, to understand how the microstructure development in these processes are controlled to achieve homogeneous mechanical properties. So in additive manufacturing, one of the prime problem with the components are actually the anisotropy in mechanical properties. So the properties may change as a function of build orientation and build directions. And due to the unfavorable microstructure development based on the direction of heat extraction. And that is a big problem, and we have been working on solving this in various types of additive manufacturing methods. Like, for example, is a powder bed system, or commonly used another additive manufacturing process is a wire arc additive manufacturing process. So what I'm going to teach is the 2 case studies. So one on how we can control the microstructure evolution during additive manufacturing, okay, in a copper-based alloy systems. In a copper-based alloy system, when we actually do welding or you do an additive manufacturing, okay, so the directional growth of grains is commonly observed, and that will lead to inhomogeneous mechanical properties based on the direction you take the sample. For example, you are building a vertical wall. The mechanical properties when you take samples along the vertical wall will be entirely different than if you take samples in, say, for example, horizontally. And the inhomogeneous mechanical properties that we get in these additive manufacturing component can lead to failure in service because of the stress partitioning that happens due to the anisotropy what we observe. One example, what I'm going to show here is how we can manipulate the process parameters, okay, in such a way that we can get an equiaxed microstructure. Okay, so the microstructure what we get out of forging, for example, or hot rolling or cold roll annealed cases, you get an equiaxed microstructure. So if we want to use additive manufacturing to produce the component and which is going to replace the conventionally manufactured component, so then the mechanical properties should meet the in-service demand, isn't it? So otherwise, it may not really advisable. And people will think that when you make a component additive manufacturing, it fails. Say, for example, you make a forging tool using additive manufacturing, and the forging tool should expect to live, say at least defined production cycles. It has to meet, say, 10,000 components. It has to produce. If it fails within, say, 100 components, so why do you want to use additive manufacturing? So the problem is, unless we understand, okay, how these mechanical properties are influenced by the microstructure, okay, how we can manipulate the microstructure in such a way that the components can meet the in-service demand. So one case study, I'm going to show you how the homogeneous mechanical properties of the printed components can be achieved by controlling the microstructure. The second case study, what I'm going to show here is, in some applications, we promote directional solidification. So microstructure has to grow, okay, in a certain orientation. For example, when we use an superalloys for high temperature applications, like for example, turbine blade, we are making using superalloy. So we expect a directionally solidified microstructure. Again, to achieve that, we need to control how the microstructures evolve. Okay, so during the deposition in additive manufacturing, isn't it? So that's what I'm going to show over here in this lecture. And if you have any questions, feel free to ask me. You just can raise a hand, or later you can ask as well once I complete the lecture. Good. So what is wire arc additive manufacturing? So I presume some of you must have already aware of this technique, or during this course of FTP, you must have also get to know about this process. So in wire arc additive manufacturing, so we use a conventional welding arc, okay, as a heat source to melt and deposit alloy wires. Okay, so what you see over this video is an high-speed video where gas metal arc welding process is used, okay, to deposit the consumables, which is here I use in a 2 wires, which is a tandem process, isn't it? So we have 2 wires simultaneously molten by the arc heat we have here, and then the molten wire is deposited. Okay, when we use layer by layer deposition, we get a component build. And if you look at it over here, so this is nothing but a welding process, right? So here we are using a single wire. So where a single wire gas metal arc based process is used, okay, to create a molten pool, and then subsequently layer by layer, if we build, so we get a component made. And since because we use arc as a heat source and we use a wire as a feedstock, okay, so this process is actually known as wire arc additive manufacturing. And if you look at the fundamental physics of this process, it is absolutely same as welding, where we use a conventional welding torch, okay, and then by manipulating the motion of the deposition, okay, we can create layer by layer multi-pass deposition. What is the advantage of this process? Because we can deposit large quantities in a unit time, and this process is widely seen as best suitable to produce large volume components, okay, with good productivity. So I see one example component printed over here. So it's a propeller, okay, with the size of about 0.5 meter, the radius. So therefore, this technique, okay, can be used to visualize, and fabricate large volume components as compared to any other additive manufacturing methods. And the other advantage over here is, so any alloy that is weldable, okay, can be used to produce components here. Okay, so and the knowledge what we have in controlling the microstructure, controlling defects, and achieving a good mechanical properties are already available in welding. Okay, so therefore we can gain the knowledge of the welding physics and translate here to develop a fully fledged near net shape or even net shape component used for in-service application. There are other advantages in this technique. Okay, so for example, here I showed two wires, isn't it? So we have a tandem wire over here. So these wires are actually deposited, okay, simultaneously. And we can also increase the productivity by using this process like a tandem wire. And we can also locally change the composition of the pool if you use a different wire by controlling the melting rates. Right, so suppose here, the classical example I showed here. So we are actually producing this component, okay, where the component which is actually over here, the inside, the rotor should have, okay, in this application, a good rolling contact fitting and good toughness and strength, okay, to meet the load. So these impeller arms, what I show over here, is actually reacting with the fluid. If it is in seabed or in sea applications, and these impeller arms are actually exposed to high corrosion environment. So it should have a very good corrosion resistance. So to print this, we can also use what is known as a functional gradation. Right, so if we can start with a steel wire, single steel wire, and slowly, gradually change the composition of the molten pool in such a way that when we come over here, so this can be a highly corrosion resistant material, say for example titanium, or we can also use a nickel-based superalloy when we actually start depositing the impeller parts. So this kind of functional gradation is also possible with a very high productivity, where the localization can be made to meet the various in-service demands that are actually encountered during in-service. If the additive manufacturing is not there and we have to prepare this impeller, first we'll have to forge this the inner part, and subsequently we'll have to make these parts also be using a casting process or any forming process. Subsequently, we'll have to weld it. Right, and then we have a dissimilar joints over here, and then subsequently, when it is actually working, we may have say failure if the weld breaks, for example. So therefore, now additive manufacturing, the entire component is actually in theoretically is made using welding, right? So layer by layer deposition. So we make this component that, and we can also introduce a functional gradation. Okay, so enhancement in performance, for example, and the advantage of controlling microstructure layer by layer. So all these things adds, and this is very attractive technique, isn't it? Okay, good. So as I said, in wire rock additive manufacturing, so we use a welding torch, a conventional welding torch to produce components. Okay, so it can be a gas metal arc based process, or even a gas tungsten arc weld process with an external filler additions. Okay, so we can add external wire and then arc heat melts the wire, and then that can be deposited. So we deposit layer by layer. Okay, so and multiple times the weld beads to visualize to fabricate the net shaped component. So most of the cases, we use a dual wire. Okay, so to achieve even higher productivity and functionalize the compositions as and when we build layer by layer. So the main learning, maybe what you can take is the wire arc additive manufacturing. It uses a simple welding torch, okay, to build layer by layer, so that the components can be fabricated using wire as a feedstock. As in the case of gas metal arc welding, the wire itself melts, and then it also acts as an electrode. In gas tungsten arc welding, so we add external filler, and then that melts and then gets deposited. Good. So the process as such, the wire arc additive manufacturing, it is not a new process. Okay, it's been considered to produce prototypes. Okay, especially large volume alloy prototypes from even 70s. Okay, so one classic example I show over here. Okay, so this is a simple rocket nozzle made using titanium. Okay, so this is one of the first applications of this conversion of welding into additive manufacturing. It happened in early 80s in place in UK, right? So where they actually converted the welding process into a net-shaped component fabrication technique by layer deposition of the weld beads, so that the CAD drawing can be visualized into a full-fledged component. And in later 90s and early 2000s, so a lot of research went in to produce an near net-shaped component, right? And from a welding deposition. And now Virac additive manufacturing also developed to the stage in such that the components are fabricated regularly, and it is also used in service applications. For example, one of the components what we have printed in IIT Madras for impeller applications, and these components, if we don't control the microstructure evolution, would invariably possess the difference in mechanical properties as a function of directions. Okay, so if you just start depositing like a simple weld beads, and then you may get the final shape of the component after post-processing machining. But then what happens when we actually use this component in service, the properties are not as good as the conventionally made component, isn't it? So then the moment you use this impeller in service, it will just crack. Okay, so much lower the service time than the conventionally made component. So then what is the purpose of using this? If a component is going to fail prematurely, then the technique what we use may not be suitable for applications, isn't it? So therefore, so we'll have to understand how we can improve the mechanical properties, especially the anisotropy we observe, right? So that's what I'm going to talk about in subsequent slides. So what material we can use in Virac additive manufacturing? So the thumb rule is, so any material that is weldable, okay, we can also use that to fabricate the component. So suppose if you want to use a material where the weldability of the material is reasonably good, and we can use that material in either gas metal arc welding or gas tungsten arc welding with filler additions, we can make component out of it. So this is a deposition of titanium. Okay, so the titanium is deposited, and you see that after deposition, if you machine the surface to improve the surface finish, you get an actual component you tend to deposit. As I said, in the first video, okay, so if you use a tandem wire, okay, and you can also produce what is known as a functionally graded material. So here the image I show you here, a nickel copper deposition is made, gradually changing the composition. So here it is not like just changing the wire at this point. Okay, so we can also gradually change, so that you start with the nickel wire, okay, and then you reach the interface, you slowly change the composition so that it becomes, say, nickel 10% copper, nickel 20% copper. Okay, ultimately it becomes 100% copper. Okay, and then similarly, you can also smoothly vary the composition by changing the melting rate, for example, so that we can get a nice functional graded material as well. And these are some advantages we gain. Okay, so in real additive manufacturing methods, where the functional gradation can be promoted, and it is not a sharp interface, so we can also change smoothly the composition, so that it is not like an actual weld. So the entire thing is weld. Entire sample here, what I show here is a weld, but the composition is also smoothly varying across the interface. Good. So the materials, any material that is weldable, we can make use of it during additive manufacturing. Okay, so what system we use? As I said, in a conventional welding system can be made use of, but we need to do some tricks, because when you get a CAD drawing, so we'll have to first slice it, okay, and then we'll have to arrive at the proper path planning. And once the path planning is ready, so we can move the welding torch in the directions what we want to create a final component, isn't it? So simple hardware what we use is a welding power source, which we require, and a robotic arm. So where the torch can be mounted onto a robotic arm, and the controller we use, and then subsequently the path planning exercise can generate the motion codes that can be given to robotic arm, and then weld position can be made to produce a final component. So as I said, the welding torch can be gas metal arc welding torch or gas tungsten arc torch with a filler. Okay, so both can be used, and then we can optimize the bead dimensions. Okay, so this is the basic of wire arc additive manufacturing. So the one is a problem I talked about, right? So I told about the anisotropy in mechanical properties in additive manufactured components. So this problem persists for any additive manufacturing process. And when we use alloys which have a tendency for directional solidification, or what in metallurgical term we call it planar solidification, so we expect inhomogeneous mechanical property. So this is one component we want to print. Imagine an impeller. It's made of copper alloy, okay, for naval applications, right? The prime problem when we actually want to print, or even when you weld the copper, is so when we have a substrate over here, so we have a substrate, so this is substrate here. So the moment you deposit a first bead, okay, the molten material which is in contact with the fusion boundary, the substrate, okay, it solidifies, okay, because of the prevailing temperature gradient, and primarily, okay, in a directional manner, a planar manner. By a metallurgical term, what we call it as an orientation relationship with the substrate grains. And subsequently, so when the solidification progresses, the grain would tend to grow along the heat extraction direction. So when we have a say pass by pass deposition, so to make this surface, so this is the cross section image what you see over here, right? So this is made using say about 15 layers. So we have 1, 2, 3, 4, 5, 6, 7. So 15 layers are there, which each layer dimensions is about 1.5 to 2 mm. Okay, so then we deposit layer by layer over here, and what we observe is when the grains grow, okay, so they grow along the preferred orientation and creating such a directionally solidified microstructure. And this is very bad, isn't it? It's an as-cast microstructure in this alloy. And if we use such a microstructure containing component, okay, so the mechanical properties, if you say apply a load perpendicular to the here in z-axis, okay, so it would just crack. It's like a wooden plywood, isn't it? Okay, so when you take a plywood, one direction you can break it easily. Okay, whereas if you break another direction, it's very difficult, isn't it? Because of the preferred orientation of the wood fibers inside. The same happens here as well, and this is what we call it anisotropy. Okay, so now if you deposit just like that and then use that component, okay, it's going to crack, because conventionally these impellers are made using a forging. Okay, so the forged component would possess an equiaxed microstructure, the microstructure what I show over here. Okay, so this is a microstructure. It is not a forged microstructure. It is an additively manufactured microstructure. By doing some trick, we can also get such a microstructure. So we need to convert the microstructure what you see over here in a directional manner into microstructure what you generally see, okay, in a forged component or in a rolled and annealed microstructure where we have a very nice equiaxed grains. So then how do we change this from here to here? Then we'll have to go back to the fundamentals. Okay, so ideally, so in a mill pool when it solidifies and a liquid solidifies, even a water when it freezes, the microstructure it forms, it is controlled by two important parameters: the temperature gradient at the solid liquid interface and the rate at which the solidification is progressing. Okay, so if you freeze the water, right, and sometimes you see very clear ice cubes, isn't it? Sometimes you see opaque ice cubes. So why is the difference? The difference is the prevailing temperature gradients inside the water when it actually solidifies. So if and a water freezes in a dendritic manner, okay, if dendrites are forming when the ice crystals are formed, you get an opaque water, the ice cube. If it is solidifying in a planar manner, in this manner, okay, so you get a very crystal clear ice cube. So why is it changing? Because the fact that when we have a steeper temperature gradient, the temperature gradient is steeper, okay, the whirlpool, an alloy, or even a pure metal, okay, solidifies primarily into a planar manner. So this is a planar solidification. So solidification just progresses, right? So slowly from here and then continuously in a planar manner. But if the temperature gradient is shallow, okay, so we get an equiax dendrite microstructure. So what you see over here. So we understand, okay, so how the microstructure morphology can change based on these prevailing conditions, right? So we can now, once we carefully mitigate the temperature gradients at the solidifying the whirlpool, we know that we can convert from planar to equiax microstructure, isn't it? And people have attempted several methods, like sometimes by changing the scanning strategies or introducing some vibrations, okay, so that we introduce more nucleations, for example, or various methods they manipulate the temperature gradient. But I'm going to tell you one neat technique. So how we have done it and then how it can be done, and people are adapting this technique as well. So this is a system what we use in IIT Madras for additive manufacturing. Okay, so this is in a simple CNC table. We don't use a robotic arm because robotic arm, there are some disadvantages than the CNC table. And then now we can also understand how the deposition happens with all these sensors and measurements attached to that. Okay, so I'm going to tell you one case study, right, in the copper. Okay, so how the microstructure can be manipulated. So what we do over here, so in additive manufacturing, so we deposit layer by layer. Okay, so we follow an like in along this X direction, we move the torch. Okay, we weave it in the welding term in X direction, and then one bead is completed, and then we'll come back. So from here, and we'll go here, and continuously we can now build a say thin wall deposition. Okay, so what happens? In the welding case, the current voltage waveform what we use is one of the important factors, because we know that the metal transfer. Okay, so when material actually the consumable melts and deposits. Okay, so the actual temperature of the whirlpool and the droplet which is actually transferred is actually determined by the current voltage waveforms what we use, isn't it? So in any welding arc welding case, we can use any constant current, okay, or we can also use a pulsing current where we can ensure that one pulse of current will lead to a detachment of one droplet. Okay, there are some other methodologies we can also use to detach the droplet, okay, from the consumable wire into the molten pool. So instead of using a free flight transfer, so what is a free flight transfer? Okay, so you see over here, so here the droplet is detached in a free flight manner to the molten pool, or we can also do a short circuiting transfer. Okay, so the short circuiting transfer, what happens here is when the droplet is actually attached and transferred to the molten pool, okay, by the dipping event, by dipping the molten wire and the droplet into the pool. And how do we control that? So the current voltage waveform what we use, so that is actually going to influence the droplet temperature and the molten pool what we actually create. We can have identical arc energy or heat input in these two cases. So if you look at these two waveforms, the actual energy, the heat input would be identical. But the microstructure what we get will be completely different. Okay, so why? Because In this case, when we use a pulsing waveform, so what we actually do that is we give a current pulses, okay, to create a high energy density arc, okay, during every current pulsing, and that would ensure that the tip of the consumable melts and gets deposited. And what you see over here is an high-speed video, okay. And during this process, we tend to also superheat the molten pool. So the temperature at the top of the pool and the bottom of the pool, okay, would be differ significantly. So that means that the temperature gradient would be steeper in this case. Whereas in this case, what you see over here, okay, the current, pulsing current we do to strike an arc would be much lower than in this case. It's about 500 amperes, isn't it? So in the pulsing case. So here we give 200 amperes current, we just enough to melt. And then when the dipping event takes place, okay, so what we also can do is during this dipping event, we transfer, okay, the droplet in much more lower temperatures. So what does it indicate? So when this transfer takes place, the top and bottom surface temperature of the molten pool would be more or less the same, or just small difference in the temperatures. Okay, you already can now correlate the graph what I showed you, isn't it? In one case, we have steeper temperature gradient. Okay, in another case, we have shallow temperature gradient. And moreover, this wire is dipping, and this is a cold wire, isn't it? So that means that during this process also, it can extract some heat from the molten pool to minimize the temperature gradient. So what happens when we do this trick? Okay, so we can deposit. So these are some of the samples. We deposit layer by layer deposition. Even the heat input can be identical. So in pulsing mode, if you look at the high-speed video and the explanation I gave you, so we have a steeper temperature gradient, isn't it? So when the temperature gradient is steeper, okay, so we tend to grow the crystals or the microstructure in a metallurgical term, okay, in a planar way. So that's what we looked at in this graph, isn't it? So when the temperature gradient is steeper, so the microstructure becomes planar, okay? In other case, so if you have a shallow temperature gradient, so you may expect a change in the microstructure. How it is changing, we'll see next slide. Okay, so when you look at this deposition, obviously this is not good, isn't it? And this is what primarily happens in any of the IT manufacturing, especially when you have a laser and powder or laser and a wire deposition. You are depositing on a substrate. So substrate is in much lower temperature. It is technically in room temperature, isn't it? If you are cooling with an effective heat transfer, when you drop on a layer of molten liquid, the temperature difference between the bottom surface and top surface would be huge. The top surface will be well above melting point, whereas in the bottom surface we expect, okay, so in a solid state much lower. So therefore, the temperature difference will be much higher, and that would lead to all the time. So we expect a planar solidification. So the microstructure would be like what is over here, and that is a problem, isn't it? Now we cannot use this microstructure in real life, and when you pull it up in a tensile mode or in apply an fatigue load, this is going to crack. It is going to fail prematurely compared to say a forged or rolled component or annealed component. And you can also see that the microstructure development. Okay, so layer bales. This is one pass layer. So when we actually solidify, so we also melt slightly the previous layer, and the grains when we grow with the steeper temperature gradient. Okay, so they grow in a planar mode by inheriting the parent microstructure orientation in the direction. In metallurgy, we call it a cube edge direction, which is 100 direction. Okay, no need to worry about it. What you see over here, it inherits the orientation and grow along this direction. Okay, so when we don't control anything, we just deposit in a conventional pulsing gas metal arc welding. Okay, so you see that. So this is what we call it a columnar microstructure, directionally solidified dentate microstructure. Okay, so it's like if you take any simple plywood, you see wood fibers oriented in one direction. Okay, so that's what we call it an anisotropic microstructure, isn't it? And the properties would be different if you apply a load along this direction, perpendicular to the fiber directions. But by changing the metal transfer mode, so what we see over here is clearly we can see the change in the microstructure. Okay, from the planar solidification, because we now change the temperature gradient during solidification. Okay, so into and shallow temperature gradient by changing the how the metal is transferred, and also optimizing the current to bring it to a much lower level so that the top and bottom temperatures differences are minimal. And that would lead to a complete change in the microstructure, isn't it? So what you see over here is compared to last, so we have a more of an EQ-axed microstructure. So this is the striking difference what we can observe by changing, okay, the fundamental mechanism by which the molten droplets are transferred. And how do we get that? By understanding the science behind it, science behind the microstructure evolution, isn't it? So now we see here, obviously the microstructure what we get is an EQ-axed dendrite microstructure. And the microstructure is as good as any forged microstructure, right? So the forged microstructure, what you see in a conventional way, would appear similar, right? That will be also reflecting in the mechanical properties. So when we look at the mechanical properties, okay, we expect that this would perform better. So what we actually, how do we achieve it? If you go deeper, so if you take now the cross section like this, and you see whenever there is a dipping event happens, there is also more nucleation happens because of the undercooling provided by the wire dipping. And in the previous case, it goes in from say layer substrate or layer bottom along the heat extraction direction. And we break that growth by this dipping event. And then subsequently, the change in the temperature gradient would also lead to the bidirectional growth from bottom to top and then top to bottom, so that now we get very fine and EQ-axed microstructure, what you see in this slide. Good. Okay, so that's what I know we can achieve, okay, by in a various strategies. And what happens in a conventional way? So as I said, in a conventional way, because of the steeper temperature gradient that is prevailing along the heat extraction direction, the grains grow, okay, in a planar way. Okay. So when we have an short circuiting or the change in the current voltage waveform with the metal transfer, so we have a shallow temperature gradient to begin with, okay, and also the during dipping event. So we also change the nucleation event so that now the grains becomes much finer, and we also break the growth of grains along the heat extraction direction. So certainly the grain aspect ratio, the EQ-axed nature of the grain changes in a pulsed mode compared to a short circuiting mode, okay. And we also get a much finer microstructure in the second case, because why? We understood how the microstructure evolves, and then we controlled the mechanisms so that we can engineer the microstructure, isn't it? So when you do a tensile testing in a conventional, the pulsed mode gas metal arc welding, the mechanical properties are different in different directions. So if you take directions in the longitudinal longitudinal directions, so the component would exhibit less strength and ductility. Whereas in other direction, you may get a good strength and ductility, but then you have a problem, isn't it? So then it is an inhomogeneity, anisotropy, what we talk about. So whereas in the EQ-axed microstructure, the mechanical properties are homogeneous. Any direction if you take, you have similar properties. And if we use this method or this metal transfer behavior for fabricating final component, it would not survive. Okay, so now we change it so that no, the mechanical properties are better. Good. So that's the lesson you want to take. So by understanding the physics, okay, so it is important to understand the science behind the the process so that we can manipulate and then achieve and good properties. If don't do that, then if you cannot just like that go and print and then use the component, it will fail. So then people will question, so why do you need to go for additive manufacturing? Because the conventionally made components are much better than the additive manufactured component. If that is the case, then what is need of additive manufacturing? Okay, so unless we address these issues, like I showed you over here, the use of additive manufacturing cannot be enhanced. Good. So this is one of the first the microstructure engineered component which we developed for Indian Navy. Okay, so it is actually now used in applications. So this is the as deposited after the surface finish. So you get the nice component. Good. So any questions so far? Otherwise, now we can go to the second case study. Anyway, we'll take the questions at the end. Not a problem. Good. So in another applications where we'll have to get microstructure exactly opposite to what we have seen in the copper. Superalloys, Inconel, for example, Inconel 625, they are actually widely used in high temperature applications and the high corrosion application, isn't it? So in these alloys, so we need to get a directionally solid microstructure opposite to what we achieved. Again, what do we do? So we can manipulate the current voltage waveforms and the metal transfer behavior so that we can get a good and a columnar microstructure. Okay, so again, we can go back to the drawing board, understand what waveforms can give us and shallow temperature gradient or steeper temperature gradient, and then we can arrive at the optimal current voltage waveforms. Okay, and then we can understand how the waveforms can influence the arc energy. Okay, and then subsequently how we can achieve the microstructure what we want. So again, one case they show comparing this waveform where we have continuous pulsing and the combination of 11 pulses, okay, and one short circuiting transfer and a complete short circuiting transfer, how the microstructure is actually going to evolve, right? So we can also again manipulate the current voltage waveforms, okay, is what we have over here, so that we can get and a completely directionally solidified microstructure what you see over here. And this is beneficial because this microstructure, a coarse grained directionally solidified microstructure, are widely preferred for creep applications, high temperature applications, because they serve better. If you have a low grind boundary area, okay, so grind boundary area, okay, if it is reduced, it's better for high temperature properties. So we can now again go back to the science of it and to understand how the microstructure can be manipulated in such that we get required mechanical properties what we have. So the waveform what I show over here, it is invented by us so that the microstructure what we actually get would be meeting the in-service demand. So what is in-service demand in this case? Say when we make a propeller using Inconel 625, that propeller, for a gas turbine would operate at elevated temperatures. And we generally have a directional solidified microstructure for the propeller. Why? Because the mechanical properties along the length of the propeller should be much better than any other direction, isn't it? So by inventing this waveform, by manipulating the prevailing temperature gradients and the solidification rates, so we can now get a microstructure which is actually directionally solidified. That's what you see over here, right? And then if you change the current voltage waveform, so despite keeping the same arc energy heat input, okay, so again the microstructure may not be directionally solidified. So what we need to understand here is the current voltage waveform and the metal transfer what we carry out, okay, so it can significantly influence the microstructure evolution. Good. So that's what I show over here. So if the current voltage waveforms are changed, the microstructure can significantly differ by the fundamental principles what I described. Good. So what is summary of this talk, what we are going to make? So we'll have interaction maybe for next 5-10 minutes, right? So understanding the physics of the process is very, very critical. Okay, so you cannot just like that go and do an additive manufacturing or 3D printing and then you expect that a component is going to survive. It will not. Unless you control the microstructure, the process parameters in such a way that the components what we make in 3D printing would exceed even the conventionally made component performance. Okay, I gave several examples, right? So forging tool, for example, if you decide to make an additive manufacturing, if it fails within one, what is the point in using additive manufacturing? So therefore, the lesson what you need to take is, right? So understand the physics of the process, okay? So that you can control the microstructures and you can get the mechanical properties. And we show that the additively manufactured components, they outperform in terms of mechanical service than the conventionally made component because of the controlled microstructure what we can generate with very fine equiaxed grains. So therefore, the additive manufacturing becomes attractive. So we also gain the advantages of directly printing from the CAD drawing. We can also introduce complex design modifications. We can also introduce channels for cooling, for example, to improve the performance in some cases where it is exposed to higher temperatures. And we can also give the gradation, the functional gradation when it grows. So all these advantages, plus we can also get better mechanical properties using additive manufacturing. Good. So with this, I will just wind up because already it's close to an hour. Okay, we will take the questions.
Thank you for the wonderful session on wire art additive manufacturing. It was like mostly people, those who are thinking about additive manufacturing, they are just thinking how to make it in a simple way. And you are very well aware, like when you go for metal additive, it is costing mostly in crores, and people want to know more about how to make the customized, like something like wire art additive manufacturing can be given better exposure on additive manufacturing. There's a question in chat box. Which type machine or process uses for machining contour surfaces?
So here we use a simple milling machine. So hold on, I'm losing my battery.
Yeah.
Yeah. So the technique what we use is simple milling. Okay.
Okay.
Yeah. So for complex closed contours, like we are also developing various. I'm not a mechanical engineer, right? So my colleagues in mechanical department in collaboration with me. So we also working in electroradiological fluid to machine the inner chambers when you produce, and we also develop new techniques using electroplasma machining. Okay, so we can also use the electrochemical methods to polish the surface, especially when we have closed contours. And these are actually working currently. A couple of my PhD students along with mechanical colleagues we are working on.
Sir, if small colleges, because like most of our participants are from private colleges, like what do you suggest to start the initial setup on wire art additive manufacturing?
So this is a welding setup, isn't it? If you have welding setup, you can start printing. Okay, so but again, it is not as easy as said. You need to understand the physics of welding. Okay, so
exactly.
You know how actually the metal transfer takes place. What is the current voltage waveform? What you use? Okay, and how we can manipulate the heat, the arc heat when you deposit layer by layer. Okay, so because heat transfer is evolving, isn't it? The mechanical and the thermal boundary conditions are changing layer by layer. First layer you are depositing on a substrate where you have a heat sink, heat can transfer effectively. Whereas if you go on higher layers, the heat transfer will primarily convective and radiative heat transfer. Isn't it? You cannot use the same heat input. Right, then you need to have a knowledge about how the heat transfer. It is again, you study everything. It is not like you're going to learn a new physics. So heat transfer is study, isn't it? Welding you study.
Okay.
Right. So you need to apply those to develop this. Yeah.
Okay, sir. And final question is like for clarity of the audience, is it
Yeah.
only specific fusion welding process can be used in wire or additive manufacturing like CMT or pulse stick or something, or every process can be used?
Anything can be used. So even you can
Okay.
also deposit using an manual metal, shielded metal arc welding. Okay, simple
Okay.
stick electrode. That also you can
Ah,
use develop. You are developing you are depositing a molten pool, isn't it? So
yeah,
it is molten metal which is deposited.
exactly.
Yes, so you can also use yeah that. Yeah.
There is a question from Dr. Kadir. How metal additive manufacturing is thermally managed?
Um, I mean, question is slightly vague. What is, I mean, what do you mean by thermal management? You talk about how the heat
Dr. Kadir, can
extraction
you
takes.
just switch on your mic and ask the question? Like,
So good afternoon, sir. This is Syed.
Good
Yes,
afternoon.
sir.
Yeah.
Actually, sir, I am trying to do additive and metal additive manufacturing for this titanium nickel alloy for shape
Okay.
memory alloys. So
Nickel
I'm
titanium. Okay.
yeah, nickel titanium alloy. So
Yeah.
probably like so thermally, like trying to control if there is any sort of distortion because I'm still in a literature study. So
See the distortion. Okay. So uh, you need to first understand how the thermal boundary conditions evolve, isn't it?
yes,
Right. So you can also control the preheating. Okay.
okay,
Or the interpass temperatures.
okay.
Okay. That will also change
Mhm.
how the distortion is evolving because you're locally changing the thermal profile.
Okay.
Yes, that is one strategy. Okay, so you can use a preheating. The substrate can be preheated. That is now widely adopted in any of the equipment. So in IIT Madras, we have a laser powder bed. So there, the substrate is preheated, especially when you are depositing materials which are susceptible for cracking or which are going to distort significantly than what you intend. Generally, the distortions are predicted using an FEM simulation, and we do correction in the design itself. So you know that you are depositing a thin wall of stainless steel, it is going to distort, say so and so mm after say 5, 6, 7, 8 layers, whatever. Okay, so then we can do the corrections in the design itself. So when you do a slicing, even before then, when you create an STL file, these are adapted. You can play around with the preheating and interpass temperatures.
Interesting. Okay.
Yeah.
Thank you.
Yeah.
Thank you. Participant, is there any other questions? Yes. Okay. If no further question, we'll wind up the session over here. Thank you, sir. Thank you so much for accepting our invitation and
Yeah. Thank
delivering a
you.
wonderful
Yeah.
talk on wire academic manufacturing. Thank you.
Thank you. Bye bye.